Hi everyone, welcome back. Today we'll be solving this Leetcode question to find the sum of distances in a tree. We'll use a technique called rerooting in dynamic programming, so if you want to learn more, keep watching to find out. The question wants us to find the sum of distances from each node to the rest of the nodes in the tree. So what that would mean, if we were to step through, would be for the first index, we want to find the distance from the 0th node to the first node, the 0th node to the second node, and of course this would be 1 plus 1 respectively, and from the 0th node to the third node, which would be this part, plus this part, right? So it would be 2, and it would be the same distance to the 4th and 5th node. So we can easily see that the sum of this should be 8. And same thing we do for the first index. So from the distance of the first node to the 0th node would be 1. First to second node would be 1 plus this path, which would be 2. And then to the third node would be 1 plus 1 plus 1, which would be 3. And similarly, we can sum it all up, which would give us 12. We can repeat that for the second, third, fourth, fifth index, which would give us 8, 12, 6, 10, 10, 10, which is the output array. Now let's see how we can solve this question from an intuitive perspective. So the most straightforward approach would be to compute the distance to all the other nodes at each node in the graph. And this can be done using any graph traversal algorithm. For example, the breadth first search, which is something that I will cover right now. If you're already familiar with this algorithm, feel free to skip this part. I'll be writing the BFS code in Java, but if you're interested in the Golang version, check out my other video above or linked in the description below, where I also use BFS for the Leetcode question Jump Game 3. So first, we want to initialize a queue of neighbors with respective to our current node. And we want to keep track of which nodes we have visited before. So let's create a set for that. Now, since we're starting from the root node and we're trying to calculate the distance with respect to that, let's add the 0th node to our visited set. And initially our distance is 0. This is kind of like the levels in our graph. So initially we're at the root level, so the distance will be 0. And of course the sum will also be 0. Now let's go ahead to push the neighbors of our 0th node into the queue. So at this point, we'll have our neighbors queue will contain 1, 2, and our visited set will contain only 0. Let's start our BFS while our queue is not empty. We want to continue checking. So we want to remove a node from our queue and make sure to check if we have not visited this node before. We want to add it to our visited set. And similarly, we want to grab the neighbors and also add it into our queue if we have not visited it before. So this is our core logic for our BFS. But remember that since BFS is also known as level order traversal, we want to make sure that we check the nodes in one level of a graph before continuing. So in order to do that, we need to grab the size of our queue at the start of our while loop. And while the size is more than 0, we want to put our core logic into this while loop. So this will ensure that we are traversing the graph level by level. Now, specifically for this question, each time we traverse the graph in levels, we want to increment our distance because this is essentially our variable that we have initialized to keep track of that. And every time we remove a node, we want to add this distance to the sum, because what we're saying is For this specific node, what is the distance with respect to our reference node, which in total will get the sum of distances to all of the other nodes in the tree given the root node 0. So finally, at the end of our BFS, we want to return the sum that would give us the answer for this 0th index. So I've written just some driver code here, assuming that we have initialized our graph, and now we just want to check for this root node 0, what is the sum of the distances to the rest of the tree. So let's just run that to check. Of course, the answer would be wrong, but what we can see here is the sum of distances from the root node 0 to the rest of the nodes in the tree is 8, which is correct. And if we look at our BFS code, with the visited set, we are essentially only visiting every node in the tree once. So each time we run this, it gives us a time complexity of O(n). But in order to get this output array, we essentially need to repeat this process for every single node in the tree, and that would give us a time complexity of O(n) squared. Now, of course, that seems pretty inefficient, so let's see how we can further optimize this algorithm. The first thing we should recognize to reduce the time complexity is we want to avoid this recomputation that we are doing at every single node in the tree. So how can we do that? We should realize that since we have already traversed the graph once at the 0th node, we would already know the distance to all the other nodes from this root node. So how can we expect this answer to now change at the first node? Specifically, we should think about how can we express this answer at the first node in terms of the answer at the 0th node. Now, if we can express that as a function of the 0th node, this would mean that given an input which we have already calculated, we would be able to find the answer to all of the other nodes without retraversing the graph again and again. Let's try to visualize things by zooming into the second node. Again, we want to think about how this answer at 2 would change in terms of answer at 0. So we want to compare how the relationship of the other nodes would differ when now we are comparing it to the second node instead of the 0th node. So we see for the first node, it's actually further away, whereas the sub-nodes 3, 4, and 5, they are now closer to the second node as compared to before. Now, let me generalize this equation. So, if we already have an answer array, this means that the answer at the ith node will be equivalent to the answer at the root node, subtract the number of sub-nodes at I. And why are we subtracting? This is because these nodes are closer, so their distances will decrease, hence minus. And we also need to add the remaining nodes because these are further away, so distance will increase. Now, the idea is also called rerouting, and I'll show you what that means with this original graph here, where each directed edge just represents a path from the 0th node to the other nodes in the tree. So what happens if we want to make 2 the root node instead? First, we need to remove 2 from the children of 0, and that means given an answer at root, we need to subtract the sub-nodes at I, and we need to add 0 to the children of 2. So we need to plus the remaining nodes. Now we see that with this equation over here, the only variables which we need are this answer at root, as well as the number of sub-nodes and remaining nodes, which can be represented by a count. So if we use this equation, we don't need to actually keep retraversing the graph again and again, and instead, we just need to do some maths with the existing variables to allow us to get the answer at all n nodes of the tree with just the given root node. Now that we have the main idea, let's code it out. I'll also be doing some visualizations so we know exactly what's happening in the code. So first we are going to need an answer array and count array as well as a tree. So let's go ahead and initialize our data structures. And of course to build our tree. So this would be our basic setup. Now let's go back to our equation from before. We see that in order for us to compute the answer at the ith node, we need to know the result at the root node as well as the count of the subnodes. So let's go ahead to do one round of DFS that will allow us to initialize these variables. Our DFS function would take in the current node as well as the parent node. And I do not need a visited set here because this is going to be a tree, so we know there won't be any cycles. Now all we need to do is, as we step through the tree, I'll check if the current node is equal to the parent node. Let's skip it. Otherwise, we want to continue processing. Now, how do we know how we should traverse the graph? So recall that the purpose for this DFS is to compute the count and answer array. And we know that the count at root is equal to the sum of the count of child nodes. So this means that our answer at root is dependent on our answer at the child nodes, which means we need to recursively traverse the graph before doing our computation. Hence, this is a post-order graph traversal. So let's go ahead and do that. Now, the count at our root node would be the sum of our child nodes, and again, our answer at the root node would be the sum of our answer at the ith node and the count. Now, I'll be stepping through this shortly to show you how the visualization would look like, but let's just leave it at that for now. Finally, when we're done with our DFS graph traversal, we need to increment the count at our node, and this is because the number of nodes at the parent would be the sum plus 1, which we want to include itself. So let's take a look at some visualizations to see how it will look like after this first DFS that we have done. Okay, let's start from the bottom root nodes first, right? So that would be one count of each node at 3, 4, and 5, obviously. And our count at the parent node for these 3 nodes would be 1 plus 1 plus 1, which is 3, but we need to remember include itself for parent nodes. So this would give us 4. Now, this node at 1, there is no child nodes, so the number of nodes at this one node is also 1. And our count at the parent would be equivalent to 1 plus 4 plus 1, which is itself. So that would give us 6. Now, let's step through the trickier answer array and see exactly what this line is doing over here. So essentially, our answer at the root node is equal to the sum of our answer at the child nodes plus the sum of the count at the child nodes. Now, let's break down each part. So our sum of the count of each child nodes essentially means the number of nodes in each subtree. And our sum of the answer of our child nodes is our subpaths sum. So we can interpret this equation over here to essentially mean the sum of the distances from node to all other nodes after this DFS would be equal to the sum of the number of nodes in each subtree plus the sum of course, the paths that we have traversed before. Let's take a look at these child nodes over here. So for these nodes, there are no subnodes and there are no paths traversed before. So the answer would be 0, and that is the same case for this node over here. Now let's take a look at this parent node. So for this parent node, we know that there are 3 subnodes given by 1 plus 1 plus 1, but the sum of the child answer is 0. So this answer for the parent node should be 3. And same thing we do for the root node, which would be, in this case, 1 subnode plus 0 paths traversed before for this child node, plus 4 subnodes over here, plus 3 paths traversed before. So in total, this root node answer would be 8. And we can move on now to the next step, which is given this answer at the root node, and now that we have initialized the count at each ith node, we can now make use of this equation to find the answer at I. And in order to do that, we basically need to do another round of graph traversal, which I'll be showing here. So same thing, we want to loop through our tree. So what we need to do now is to translate this equation to code. And what we see from here is that our answer at the child nodes is dependent on our answer at the parent node. So this tells us that we need to do pre-order traversal for this DFS. So first we need to compute our answer at I, which would be equal to our answer at the root node minus the number of subnodes, which is a count at I, plus our remaining nodes, which would be the length of count, and that is n, minus our count at I. Then finally, we recursively continue our DFS since this is pre-order traversal. Let's visualize exactly what's happening with the second DFS. So this is the original answer array that we got following our first graph traversal, and we want to make sure we start our second DFS also from the root node. So let's see the result from the first iteration. At index 1, the answer would be our parent node result minus our count at node, which in this case is 1, so minus 1, plus n minus the count at node, which is also 1, multiplied by 1, because every other node for the remaining nodes are getting one step further away. So if we were to compute this, this would give us 12. Now let's see if we were to step through the rest of the indices. We'll see that for the second index, the answer would be 6, and that is because we take the parent result, which is 8, minus 4, that is our count, plus n, which is 6, minus 4. And similarly, the bottom nodes would give us 10 because we have 6, which is our parent result, minus 1 plus n minus 1. 1 is our count at this I. So what we observe here is also in order for us to compute the result for the child nodes, we need to know the result of the parent node. And that's why we need to do pre-order traversal in this case. So let us return the answer and run this code that we have written. So it's accepted, and we see that for this algorithm, our time complexity for each DFS is OM. So that would still give us an overall time complexity of ON, which is a huge improvement from our previous ON square time complexity. Thanks for watching till the end. If you like this video, check out my Leetcode playlist and subscribe to my channel. I plan to do more Golang projects and tutorials. See you next time!